introduce today's speaker, Sid. Sid is an Eric and Wendy Schmidt AI and Science Fellow at the University of Chicago. He received his PhD in computational modeling and simulation from the University of Pittsburgh, where he worked with Professor Carl Johnson. And this is why we know each other. We went to the same school, basically. And he worked on machine learning interatomic potential and reactive molecular modeling. He also received his master's from Carnegie Mellon University, where he worked with Professor John Kitchen. His research now develops theoretical, computational, and AI-driven frameworks for understanding reactive molecular systems and complex energy landscapes across chemistry, biology, and material science. And as a Schmidt Fellow, he co-leads the development of Gentlest Ascent Dynamics enhanced sampling, where he will speak about it today. And his broader interests span statistical mechanics, quantum chemistry, enhanced sampling, data-driven modeling of reactive and soft materials. And with that, I'd leave the floor for Sid to talk about his research.
Yeah, thank you so much, Mona. It's nice to see you again. Can you guys hear me now? Is it clear? Okay, yeah, perfect. So, I am an AI Schmidt Fellow at the University of Chicago. I work with Professor Andrew Ferguson, who is in the Pritzker Molecular Engineering Department, and the topic is on gentlest ascent dynamics for rapid exploration of energy landscapes. So, um, so all of this is possible because of my collaborators, Armin, who's another postdoc in the lab, Trung, who's part of the the research center for computing in University of Chicago, and Andrew Ferguson, who's my PI. So let's dive into some of the science. So we start with this question of what are the limits of molecular simulations, and for that we can you can bring about this nice review article called Molecular Dynamics Simulations in Biology by Martin Karplus and Gregory Petsko, where they list out that two limitations in existing simulations are these approximations in the potential energy functions, and the second thing is the length of the simulation. So the first introduces some systematic errors, and the second introduces statistical errors. So what this means is, wait, what happened to the slides? Okay. So what this means is that we have systematic errors through through your force fields, the force fields that you pick, and statistical errors comes from the from sampling sampling your configuration space. So for you can either tune either of these in order to make your simulations better, but what we are focusing on is the second part, which is on statistical errors. So statistical errors, to mitigate them, you would need to do good amount of sampling. So what about sampling? So if you start with this molecular system that lives in this, we know that these systems live in very high dimensional free energy landscapes. And typically traversing these systems are quite complicated because you come across rare events that control kinetics of the system. And the reason why it's difficult is because of these transition states that most of us are aware of. And what typically happens in while you're trying to perform sampling is you're stuck in these basins. And typical ways of sampling these molecular states could be using standard molecular dynamics, where again you're stuck in these energy basins, and the sampling is now again exponentially suppressed by the barrier. The reason is because your your space is now determined by this or controlled by this Boltzmann distribution, where the probability of each state is proportional to the exponent of some free energy surface. So the question now is how can we effectively escape these Boltzmann basins that are offered to us, right? And why does it matter? Is because we see this in material science, we see this in biology. Say, for example, if you look at solid electrolyte interfaces, or you can even consider dynamic catalysis, ionic liquids, or protein folding. All of these have the same underlying problem, which is systems evolve on rugged free energy landscapes with long-lived metastable states. And the transition between these states are rare, thermally activated, and the standard molecular dynamics may not be suitable because it can get trapped in these basins. And the challenge is again not computing the energy, but discovering and crossing these relevant saddles or these transition states. So there are several approaches that already exist. So some of you might be familiar with uh, CVs, which are collective variable based approaches. So CVs are just low dimensional functions of atomic coordinates that capture slow transitions, and these could be defined through some simple trivial functions like the bond distances, dihedrals, or principal components of some trajectory that you already have. And you can use these collective variables to then bias along these collective variables to then recover your free energy surface. Some examples could be umbrella sampling, where you deposit or you set up different umbrellas where they all overlap with each other from one end of your collective variable to the other end. Or more recently in the past decade has been metadynamics, where you sequentially keep depositing biases so that you escape your transition states. And this bias deposition is also tempered, and there's some history dependence on it. This is all great, but these methods presupposes some a priori availability of a good collective variable, because a poor collective variable can distort or even give you orthogonal barriers, which is not may not be physical, may not be useful for your case. There could be issues of degeneracy with your collective variables. So the obvious thing to think about are these CV free methods. So you don't really have to deal with collective variables. But in fact, these CV free methods are a lot of them are older than CV based methods. So CVs are a solution to these older approaches. And some of these could be tempered, like these are typically called tempering approaches, where you modify the temperature or the Hamiltonian itself to accelerate barrier crossing. And some examples of CV-free methods are, simulated annealing or replica exchange. And here's just a visual of what happens in replica exchange. Say you want to get like a thermodynamics of this low temperature, so T1. What you typically do is you make multiple copies of the same system and all simulate them at different temperatures, and then use a metropolis criteria to exchange states from one temperature to the other, and this enables quicker sampling at this lower temperature. But if you think about this, you have substantial CPU time being expended on these conditions that are not of direct interest. In order to get good sampling at your low temperature, you end up simulating these four or five or sometimes even 10 different temperatures of the same system, which could be really expensive. So, which means we go back to our CV based methods. So, how do we construct a CV? So, you can craft a nice CV for very trivial systems, but most chemical systems are actually not trivial. Just handcrafting them may not be as easy as it sounds. So there are data mining or dimensionality reduction methods that can discover these good CVs, where they are separated through some metastable system states. Um, you can characterize important large scale or slow conformational motions. So slow conformational motions go along from one basin to the other basin because there is a barrier, and large scale or high variance ones are the ones like say PCA, for example, are these regions of with the highest spread. And these are explicitly differentiable functions of atomic coordinates, which is one of the criteria or is a requirement for these collective variable based approaches. Now, so what we know is now we can learn collective variables given trajectories, right? But where do we get these trajectories from? So the goal is, say you have some simulation trajectory. Is there a one shot post hoc projection of this long simulation trajectory into this collective variable embedding, right? You can do one thing. You can run unbiased simulations. These would take forever to run, or you can use bias simulations and keep updating keep updating and finding or expanding your collective variable itself. But again, how do we go back to getting these trajectories, which becomes a chicken and an egg problem, where the chicken is you need good collective variables um, to drive sampling of configuration space, right? And the egg is these trajectories with good sampling are needed to discover good CVs in the first place, right? So where do we start with? So in this, what this project is trying to do is to come up with the best egg, which is trajectories with good sampling. So that once you have good sampling, I can just do this thing that we dreamt of, which is use the good sampling, directly find out CVs, and then do whatever physics that we want to do later. So for the first step of the solution, we can think of the this landscape geometry view, going back to the same simple energy function that we have. The simplest form of the steepest descent dynamics associated with this energy function v can be given by this easy differential equation, where the solution, if x is a solution, then v of x of t is a decreasing function of t. So basically you see it going and converging to a local minima if you have an infinite amount of time, right? But now we are not interested in the local minima. What we're interested is in the opposite dynamics, right? We do not want to go back to the basin because basins are what keep us trapped, but we want to escape the basin or do an ascent, right? And so for that, we'd have to think about how to escape the basin. So how do rare events typically occur? Through chemical reactions and conformational chains. And these transitions occur through index one saddle points, this Pringle looking shape. So, and these index one saddle points are recognized as characterized by a Hessian, which has exactly one negative eigenvalue. So this goes to the next concept, which is okay, I know what direction I want to go. What if I just take the inverse of this and try to perform my dynamics now? Well, what can happen is you only find local maximas which are not of interest to us, right? What we want to find are these saddles. So this is where this gentlest ascent dynamics concept comes into play, where the dynamics climbs out of these basins of attraction, right, in a gentle way. And I'll talk about what this gentle means. And finally, it converges into index one saddle points in this energy space. So this was developed by this concept is not very new. It's developed about like 15 years ago by Weineni and Xiang Zhao. Weineni when he was back in uh, Princeton, and Xiang Zhao when he was in Brown. And what this does is you have these two dynamical equations. The first equation is the same thing that we saw before, but it has an additional force term, right? And the second equation, I'll talk about this later. So let's talk about what the second term over here means. And these entire two coupled equations are part of the gentlest ascent dynamics. So the second term is this force component along the softest direction. Now, what does the softest direction mean? This means the force that is projected along this vector v, and this vector is the eigenvector of the smallest or the most negative eigenvalue, lambda 1 of the Hessian. Now, Hessian, it's this is something that we already know. Hessian is calculated as using this equation over here. What you then do is just do an eigenvalue decomposition of this, sort your eigenvectors out, sort your eigenvalues out, and get the eigenvector that corresponds to the most negative eigenvalue, right? And you just project your forces along this eigenvector, and then you remove that much amount of force from wherever you are, from your current force at that given state. And there is another equation which is this differential equation for this vector v itself, where instead of calculating the whole Hessian, what you can do is you can relax this equation. You can relax um, this this vector v to the softest eigenvector, right? Now, you can, it's not necessary to maintain both these equations. You can just remove this out entirely, which brings you to an idealized saddle point dynamics, which is exactly the same thing. But instead of having these coupled equations, you now just calculate the full Hessian and then you diagonalize the Hessian, get this V, and then project your forces along this V and remove that much amount of force along from that direction, right?
Wait, am I crazy or it looks like you're adding that much amount of force, right? The plus sign?
Oh yeah, yeah. It's like if you think of this as F, negative of the grad with respect to V as F, so this becomes negative of that value. So like this is negative of a force, right?
Yeah,
So
okay.
it's
That makes sense. Yeah.
yeah, yeah. Yeah, it's I think the term so when you so when you when I that's it's a good question. And when I say remove, what essentially I'm trying to do is if I'm at any given state, if I if I see this this V, right, this eigenvector, it tries to find the direction of this like softest ascent or gentlest ascent. It's called the softest direction, and then instead of instead of uh, going or instead of experiencing force, what it does is removes not once but twice. So it basically makes it into converts it from an ascent to an attractor, and basically tries to go down towards that direction, if that makes sense, right?
So, but okay,
Yeah,
so
yeah,
say soft is like if you have a very large negative eigenvalue of the Hessian, that's a really high frequency mode, right? So what
right.
so like it's not very gentle if you have a very large negative, like highly negative eigenvalue. So what do you mean by smallest?
So it's the one that has the least curvature, but towards a positive, like towards the ascent direction. Does that make sense?
Okay, so it's the smallest absolute eigenvalue.
Yes, that
Okay,
should be correct. Yeah.
okay, it's just confused. Okay, gotcha.
Okay. Um, so yeah, so the plus two term over here flips the sign of the component of the force along this V, right? And now this creates an unstable flow along the softest mode, which is going to be a ascent, and a stable flow along all other modes, which is going to be a descent. And this results in finding the finding and relaxing towards the saddle point itself, right? So essentially this is like a paper from Mark Tickerman's lab, where they used this gentlest ascent dynamics to relax to saddle points, like these green points over here. Okay, but it's good that we can find these saddle points, which is great. But our objective is not just to find the saddle points; it's to find the saddle points and then to go past it and find the next basin, right? Because what we are trying to do is come up with good collective variables that explore the entire potential energy surface in a more effective manner. Right? That's part of the egg that we're trying to solve. So the whole project is just trying to make a simple fix to what is already known. And so now this is your the idealized saddle point dynamics equation. And you make a small change, which is you just make this as a tunable parameter called kappa. That's it. And now you have this controlled inversion, and kappa can be any value of your interest. So this just for an intuition, if you set kappa equals 2, it's going to be a full inversion. So gentlest ascent to you start making it into a descent, which is your traditional gentlest ascent dynamics for saddle point searching. If you set kappa equals less than 1, then it becomes partial inversion. And if you can set kappa equals 0, it becomes normal dynamics. Kappa equals less than 1, your barriers are flattened but not fully inverted, right? Why less than 1 and why not kappa equals 1? Because ideally if you have kappa equals 1, you're just making it fully flat, and uh, you can hopefully have like an easy path or easy jump from your one metastable state to the other metastable state. But what typically happens is there are these diffusion controlled dynamics that happens rather than drift control dynamics because of this entire flattening. And typically this leads to excessive wandering near the saddles, and it doesn't really find the basins at the right time. So if you just set kappa less than 1, you have this partial inversion. So effectively you're not making this entirely flat, you are retaining some of the downhill drift, so the basins are still remain metastable, but these drifts are weakened along these softest escape routes. if that makes sense. Now we have these gentlest ascent dynamics trajectories. It also gives us some information of how you bias the system along your simulation. Can you use this bias data to recover your unbiased free energies or unbiased thermodynamics? The answer is no. The reason is because the forces that are incurred are non-conservative, which means if you go from path A to path B through different paths, point A to point B through different paths, the work done is not equal through all these different paths, and which means the integral in this closed loop is not exactly zero. It would have been nice. It would have been nice if this worked out, because a lot of biased MD based simulations like metadynamics itself, you deposit bias, but the forces are conservative, so you can use the bias data to unbias the system and get your true free energies. But now what we have is we have a mechanism to navigate through these soft modes to hit metastable states without any a priori knowledge of the system. All I need to do is start with the reactant or start with some state, and it automatically finds all of these different states by just going through these softest modes. But now the goal is, can we how can we learn our collective variables and try to go to the next step? So for that we have a two-phase solution. The first phase is take some system of interest, perform gentlest ascent dynamics, you bias the system, you get some trajectory that has explored all of your basins. Then you perform dimensionality reduction on it, which gives you some collective variables. And then you use the collective variable based sampling, like the metadynamics and umbrella sampling that I spoke about, to bias your system again, and then get back your thermodynamics or structure of interest. So this is going to be a two-phase solution instead of just having a one-phase solution. So we will start off with a simple example of a Muller-Brown potential.
Ted, can someone ask the question?
Go ahead.
So when you're doing this sampling, is there any sort of, I guess you're taking multiple of the softest modes and exploring them all, is that correct?
So multiple softest modes and exploiting them all, that's correct. But at each state, there's going to be only one softest mode.
Right, but you're not just taking the softest one. You're taking like a few of the softer modes. And I guess, like, how do you decide how many soft modes, or like what is enough for an adequate sample?
No. At every point, we only pick the softest mode. That softest mode can change if you, at state t equals t1, a softest mode could be some eigenvector, right? But at t equals t10 or something, that vector could change. It just could be in a different direction. That's all. So you remove that much amount of force from that direction. But we only pick the softest mode.
Yeah, I'm a little confused. So what prevents you from just going to back the way you came? Is it just momentum? Like, because the softest eigenvector will point in the same direction, kind of,
So, what's the limit? Like, what prevents you from going back to what again?
So if you start in basin 1 and then you follow your soft mode, you get in basin 2, but the softest mode might still be the way you came from, right? Like, so what prevents you from just hopping back to where you came from?
Oh, so you're trying to get back, like you're trying to ask like question regarding this, in terms of like why is the work different?
No. I'm just like the sampling between basins. Like, won't you return to basins you already sampled?
Yeah.
Okay, well, like
Wait.
what's yeah.
No, I think I couldn't hear you for like the last few words or something. Sorry.
I'm saying, well, you would return to basins you already sampled eventually. I mean, at least, like, wouldn't the softest mode be the direction you came from? I mean, so it must be just momentum that carries you to another basin entirely, right?
Yes, it could be, yes.
Yeah, okay, that's fine.
Okay, so we start with the Muller-Brown potential, which is like just this two-dimensional setup that you have over here. and it's just an exponent of some of these terms over here. It's a fairly simple potential to look at, and it has three different basins now: A, B, and C. To go from A to B is like a hundred and over 100 kT. To go from B to C is about 8 kT. So it's a smaller barrier. And the reason why you pick this is because it has you can have analytically defined multi-basin landscapes, and we have well characterized minima and saddles. And another, I think the challenge is like you have no trivial reaction coordinates, which is quite different from collective variables, but it is not straightforward to come up with a function that can go from A to B directly. So let's start off with just by doing an unbiased dynamics, using starting from the state A, and operating at a temperature of 2 kT. We compute something known as the mean first passage time, which is the expected time or the number of steps a stochastic random process takes to reach a specific target state or boundary for the first time. It's called MFPT. And it comes out to be 10 to the power 20 time units, which is very high, and it becomes very becomes quite infeasible for most of our simulations. If you just run like for 100,000 time steps, you are still stuck in this state A. Now you apply GAD or Gentlest Ascent Dynamics onto this, and if you try plotting delta F, which is just the GAD forces at each point in space minus the actual forces that you get, what you see over here is the forces inside the basins are unchanged, but the forces near transitions are the ones that are that have these higher magnitudes. Yes, was there a question?
No, you're good.
Okay. So now if you compare the simulations for the same amount of time, 100,000 steps for an unbiased simulation, 100,000 steps using your GADES dynamics, you see this being stuck at this basin A, but with GADES dynamics, you explore all these basin A to B to C. And the kappa that we picked, if you remember from before, was kappa less than 1. So we picked 0.9, which is partial inversion. And this seems to explore all basins within the simulation that we have. And the cool thing is, again, you do not need information how the final basin looks like. You only need to start at some basin, and then it automatically explores these other basins by itself. So fine, we have these amazing Gentlest Ascent dynamic trajectories, but now how can we learn collective variables from them? So this has been a field that people have worked on for a while. Our lab, for example, in the Ferguson lab, they've spent quite a lot of time and effort in coming up with different methods. So there are two main classes on how you learn collective variables. One could be high variance modes, or one could be the slowest modes. And for both of these, you have linear or nonlinear approaches. So like something that you would have definitely seen is PCA, or maybe for a slowest linear mode could be Tika or MSM, for example. There are other nonlinear modes like the diffusion maps, or even something known as deep Tika, just a regular Tika but with a neural network involved. These are also called SRVs, which is developed by the Ferguson lab. And so for this project, we made use of SRVs for some of the systems. So for phase one, if you remember from the overall two-phase diagram, is start with the GADES trajectory, use some CV learner. In this case, it's going to be SRV, state-free reversible VAMP-nets, and try to learn the leading eigenfunctions that correspond to the slow modes now. These are not, we've forgotten about soft modes. Now it's going to be just the slow modes to go from one state to the other state. And if I take the same XY space that we saw before and try to just plot the psi1, which is the first slowest mode, what we see is that there is a negative to positive shift in this first eigenfunction from basin A to basin B, which means that this first eigenfunction is able to pick this first slow mode. If you remember, this is about 100 over 100 kt, and the second slow mode is able to see the sign change from basin B to basin C. So, which means that the psi1 and psi2 are potential good collective variables to then perform and go to phase 2, right? Phase 2 is going to be use these leading eigenfunctions, then use some off-the-shelf enhanced sampling methods like metadynamics, deposit biases along these psis, and then try to recover and get your thermodynamics like the free energy surface. And we were able to do this exact same process. It was we recovered a free energy surfaces for this MB, which is a Muller-Brown system with GADES, and these barriers match with the reference barriers that we had for our system. And in this case, I think because this is a two-dimensional system and on just a single particle, we would not have entropic effects. So the free energies would just be the potential energy surface itself. So it was great to see this toy problem, but like what happens if we take systems of actual value like atomistic systems? So we started off with this molecule or this 9 residue peptide called AIB9. It's a biomolecule and it's composed of this alpha amino isobutyric acid, this is what is AIB stands for. And it has this chiral inversion from this fully left-handed state to a right-handed state. It has a bunch of this very rich and complex conformational dynamics, and it has these two well-defined states. So it seems like a nice candidate to work with. And there have been quite a few labs who are trying to come up with ways to sample these kinds of complex molecules quite effectively. And if you see over here, it has 4 metastable basins. So the first one is just the left-handed state, right-handed state, and has these 2 pathways. One is the left-handed activated state and the right-handed activated states. There's also this group from U Chicago, Aaron Dinner's lab, who's come up with these ways to characterize how this molecule appears. So this chi over here are just linear combinations of the sign of the dihedrals of this molecule, and chi1, for example, chi1 just measures the chirality of a configuration from this A state, which is your left-handed state, to a B state, and chi2 measures the difference in the chirality between the two halves of the molecule. So this is obviously much more difficult problem than the Muller-Brown potential. We're considering all atoms with explicit solvents, right? So remember that this GADES needs or requires this calculation of Hessians, right? This could be very infeasible to calculate the Hessian of this full space. But the cool thing is the Gentlest Ascent Dynamics does not require calculation of the full space. You can just calculate the Hessian of the subspace. And so to pick the subspace, what we did is we picked the 9 alpha carbons. So these alpha carbons are these atoms in black over here, these carbon atoms. And that corresponds to a 3n by 3n matrix, which is a 27 by 27 matrix. Instead of, if you took the full Hessian space, it's going to be 14,000 times 14,000 space, which is again very difficult to handle in the first place. So we performed our Gentlest Ascent Dynamics and compared it with unbiased trajectories. So these are some of just projections of this simulation on 18 dihedral angles that corresponds to all the 9 residues from AIB9, and each plot is for each of the residues from the same simulation. We see that the unbiased simulations tend to be stuck in some of these basins over here, but GADES just finds all of these left-handed to right-handed and these activated states as well. And going to phase 2, again, GADES trajectories to some CV learner, in this case SRV, and then get the leading eigenfunctions. And so this one over here is what we got as part of our results. And our SRVs, which is the first eigenfunction was able to find this full chiral inversion from a fully left-handed state to a fully right-handed state, and this is just a reference that I was showing from the paper that is referred over here. So for phase 2, again, start with the leading eigenfunction, perform metadynamics using these eigenfunctions, and recover the free energy landscape. And what we see is, these are still running. I think there's some of these states are still yet to be explored, but they would probably be explored in like the next half of a day or so. So apologies for this plot, but what we typically see is, with these new collective variables, our gates can sample these low energy ground states, that's the L and R's, and also get your excited states. And so the CVs using SRVs provides barriers for these excited states, which is quite difficult to do without it. Second atomistic example is this molecule called the HIV-TAR RNA. So basically the folding and unfolding of this RNA molecule. And the reason why this HIV-TAR RNA is important is because it's a regulatory control element essential for viral replication in our body. And it in terms of the physics, it has a complex folding and unfolding process. So this is not only determined by the nucleotide sequence, but also by the cations that you add that you have in your environment to soften the electrostatic repulsion interaction between the negatively charged phosphate groups. And it's typically, I think you add like calcium ions or something like that on the sides. So the understanding of this molecule is important because it helps in stabilizing your secondary and tertiary structures. So this is just your fully folded structure. You can have multiple different structures which controls controlation. So
I think it is frozen.
Frozen.
Yeah. It's
phosphor groups. Oh yeah, is there a question?
said you were frozen.
Okay, can you hear me now?
Yes, we can now.
Okay. So to get an empirical picture of like what really is going on in terms of a folding and unfolding process, we project all of our simulations into this empirical coordinate, which is called a D tail. The D tail just means the tail end-to-end distances of the RNA, and the D hinge is just the distance between the phosphor groups somewhere over here, close to the hinge of the RNA. So with a 10 nanosecond simulation, we see again GADES tends to explore multiple different states, not just the initial started folded state. It goes to these different misfolded states and also some unfolding states as well. And the unbiased typically tends to get stuck in this folded state. So we start with our GADES trajectories, do the same mantra that we had before. Learn our collective variables, pick the leading eigenfunctions, and try to see if the eigenfunctions have some physical meaning. And if you just like plot these first two eigenfunctions from SRVs, that's the first and the second slowest modes, and you try to color them based on these empirical coordinates that we know, the D hinge and the D tail. We see when you start with this fully folded state, we can get to what's happening. Just a second. Yeah. We can get to these complicated secondary motives or these misfolded states, and these typically go through a barrier of 20 kilojoules per mole. And these barriers in fact match with what is already there in literature. So effectively showing that this Gentlest Ascent Dynamics can be quite useful for such complicated systems with explicit solvents. Now we try to use try to simulate a different third example where you have a more reactive potential energy landscape. So this is an SN2 reaction. It's a one-step organic reaction where you have a strong nucleophile that attacks an electrophilic carbon from the backside, while a leaving group simultaneously departs. So it leads to like a simultaneous bond breaking and bond formation reaction. And there is a strong charge redistribution along this reaction pathway and a narrow transition state region in the configuration space. So, and also this builds a case to model with some machine learning interatomic potentials. Specifically, we make use of UMA, which is a universal model for atoms, and this is something that we are working closely with Zach Olisi in at Meta. And the reaction is quite simple. You have a CH3F group and a dangling chloride ion, and there is a concerted hop that happens where you finally get the chloride ion attached to the CH3 group, and the fluoride ion just keeps roaming around. So there are, again, we could have used these nonlinear methods like SRBs, but what we try doing is to show that even linear methods like just regular time lagged independent component analysis is quite useful. In fact, you can just use the regular PCA and call that your corrective variable, and show try to get some thermodynamics out of it. So GADES trajectories, Tika to leading eigenfunctions. If you just perform your GADES trajectories and try to color code them based on the first tick, that is your first principal component, we see that there's a nice sign change from this first basin where you have a CH3Cl to the second basin where you have a CH3F being formed, and the other modes, maybe you can project it to several different modes. The other modes could just be simple vibrational modes with the CH groups in this SN2 reaction. And now the thing is, again, just try to pick these different components and bias along these components and try to recover the free energy surface, as we've done for all of these